Hello, this is Jennifer Martinez. In this video, we're going to interpret the derivative. But before I do, I would like to go over an alternate notation. And this is the first paragraph from our textbook for this section. So I'm going to go ahead and read this. So it says, so far, we have used the notation f prime to stand for the derivative. There's an alternate form. It's going to be dy dx. And it was introduced by a German mathematician, Leibniz. What he did is he chose a variable y or whatever to depend on a variable x. So if you have y equals f of x, he wrote dy over dx for the derivative. This is going to be quite useful because it's going to help us to interpret the units or interpret our derivative because it shows us the units. It makes the units quite visible. Leibniz notation is quite suggestive if we think of the letter d in dy dx as standing for a small change or small difference in. For small changes in delta x and delta y, we saw this notation because we saw that this was really, if we looked at the slope of the secant line, it was the change of y over the change of x, delta y over delta x. That's what it was. And if we looked at the limit as that delta x went to 0 of that, that is a definition of the derivative. So this notation reminds us of that. It reminds us that the derivative is the limit of ratios of this form as the delta x goes to 0. I know this is not the formula in the book, but we've seen this before, but let's go ahead and do it again. Let's make this x. And what the book likes to use is h. What is h? H is going to be some distance here. Let's make this like x plus h. H is our delta x, so you can see that because this is x plus h. Delta x is x2 minus x1. So if I subtract these, I do indeed get h. And so there's an h in the bottom there. And then this right now we know is f of x. This one, the y value for this, is just f of that, f of x plus h. So if I take y2 minus y1, I would get f of x plus h minus f of x, which that is the formula in the textbook. Although this is not formally correct, it can be very helpful for us to think of dy dx as a small change in y divided by a small change of x. So that is when delta x is very small, as it's really as the limit it goes to 0, but as it's really small, it's approximately the same. And if you remember the rate, this dy dx, this is going to be the rate of change. That's what that's going to mean. So it's going to help us to interpret the derivative because we know it's a rate of change, and now we know the units are going to be the change of y and the change of x over the change of x. So let's use these units to help us interpret the derivative. And let's start with example 1. It says the cost of extracting T tons of ore from a copper mine is some formula which we don't know, C equals F of T in dollars. What does it mean to say F prime of 2000 equals 100? So since C is the cost in dollars of extracting ore from a copper mine, and T is the tons, here it says tons, the amount of ore in tons, we can now look at F prime of 2000 using this new notation. So we're going to say it's going to be dy over dx, but the y is in this case the c, and the x is the t. What I'm going to do is I'm going to draw a line to represent that 2000. The book uses this notation, and they say that that is going to be, the 2000 is the t, so they just put t as 2000 here to help us. And we know that is 100. And so this approximately represents the change of cost. This represents the change of tons. So the units, let's do units first, is this going to be in dollars per ton. There's the units. So that's what it means. What does the 2000 mean? That's going to be how many tons that we have. So right when we're at 2,000 tons, it tells us that the rate of change is $100 per ton. So that is the answer. The rate of change is $100 per ton, because that's what it means. It means rate of change, right? There it is, rate of change. When 10,000 tons of ore has already been extracted right at that point from the mine, that instantaneous rate of change. Another way of looking at this is looking at just the change of C over the change of T, right? That's this idea. That's what's approximately equal to, as long as the change of T is small. And we know this is approximately, let's just say approximately, the derivative, which is 100. That is in dollars per ton. So you can see here that for each additional ton, right after the 2,000, for each additional ton from that point, the additional cost is going to be $100. So again, when 2,000 tons of ore has been extracted, the additional cost of extracting the next ton is approximately 100. Or you could even think of it like this. If I take this as approximately again, multiply both sides by delta t, 100 times delta t. This is the additional cost. A small change of t is what this one is. So you can see here that when we add one additional ton, the additional cost was 100. And we could also say, we can do that for any value. So you have 2 additional tons. For the next 2, the additional cost would be 200. So you can see here that the derivative, 100, acts as a multiplier, converting tons, right, the change in tons, into the change in dollars, the additional cost. Okay, let's do the next example about fuel efficiency. If G of V is the fuel efficiency in miles per gallon of a car going at V miles per hour, what are the units of G prime of 90? And what is the practical meaning of G prime of 55 equaling negative 0.54? A lot of miles per hours, miles per gallons going on there. So let's go ahead and try this one. So first I would like to get a hold of what are the units. Let's take care of that first. So to use my new notation, I'm going to let Y equal G of V. And G of V is, again, the fuel efficiency in miles per gallon. I'm going to call that MPG for short, of a car. And V is the speed of the car in miles per hour, and I'm going to call that MPH. So what is G prime of 90? Using the new notation, dy dx, so be dy dv, again, at v equals 90. So that means at 90 miles per hour. And what's this going to be? Well, they didn't give us a value here, so they just asked for the units. So this is, the units are going to be, is in, what is it? Miles per gallon per miles per hour. Yeah. It's a lot of rate of change here. You can actually manipulate this and reduce it if you want to. But this is going to be more useful to us in our practical meaning. So I'm just going to leave it like this. That is the answer. Okay, now let's look at G prime of 55. We never used that 90 miles per hour, did we? This one we will. Let's see, that's going to be the same thing. But now V is equal to 55 miles per hour. And they give us a value for this. Okay. And again, it's the same units. Miles per hour, or miles per gallon, per miles per hour. So what is the practical meaning of this statement? So you can see here, it says it all right here, at 55 miles per hour. So right when you're going to 55 miles per hour, the rate of the fuel efficiency is negative 0.54 miles per gallon for each mile per hour increase. Oh, by the way, decreases. I didn't say the word decreases. Decreases at 0.54. The negative tells us it decreases. So let's go ahead and see that here. When a car is traveling at 55 miles per hour, the fuel efficiency of the car decreases by a rate of 0.54 miles per gallon per miles per hour. That's another way of saying that. Or you could say that the fuel efficiency of the car is decreasing, and it is decreasing at a rate of approximately 1/2. I gotta get 1/2. Well, this is about 0.5, so about 1/2 the miles per gallon as the velocity increases by 1 mile per hour. So for each increase of velocity, when I go 56 miles per hour, for each increase, the fuel efficiency is going down. That makes sense. It's going down, and it's going down about a rate of half of the miles per gallon. Interesting. So you can see here, if I make this smaller so you can see the whole thing, you can see here that you can use this new notation to help you with the units and to help you interpret what that rate actually means. See you next time.